All right, so if you take a look in the lesson 2 notes, up at the top, I gave you the general form of a quadratic, correct? F of x equals ax squared plus bx plus c. We should be on the page that says unit 2 notes at the top. Okay. Right? Is that what you have up there? Yeah. Okay. So if you remember, when we talked about this, we don't know if a is 1 or 2 or a fraction or something else. So we're going to assume that a is not 1 and go through the process. When we do this, step 1 was to take the first 2 terms. Do you remember how we separated them and factored out the a value to make that coefficient of x squared a 1? Yes. Well, we're actually going to just take a out first. So notice I boxed these 2 terms together. I'm going to take an a out, which is then going to leave me with x squared plus b divided by a, x, plus c. You know that when you GCF, you actually divide out. It doesn't go away, it becomes the GCF out front. So, in a very broad sense, somebody want to fix their phone?
I don't think that's a truck. That's not a truck. That's not like beep, you're backing up.
Okay. No, it was a truck.
It wasn't.
Okay. All right, so my first question is this is a very abstract algebra concept because we're not using numbers. Does that make sense to you when we factor out an a, that's what it would look like? Like just in general. Okay, so if we follow suit, b over a was what I always called like the b term before. So over here, maybe I can do it up here. If I have x squared minus 6x, and I want to complete the square, I would take the coefficient of the x term, the linear term. So this is my new linear term, and I would do what with it? Divide by 2, and then square it. Okay? So, for instance, I would divide this by 2, and then I would square it, correct? And that would give me a plus 9 to complete my square. Those of you that were here, does that look familiar? We did that as the warm-up. Okay, so now if we slow that process down, slow your roll, do the same thing here. Take b over a, divide it by 2. Okay, so here's your b over a, which is the coefficient of x, divided by 2. From the prerequisite unit, if you recall, we put this over 1. How do we take a fraction and divide it by a fraction? We multiply b over a by what? 1 over 2, which gives us what? B over 2a, correct? So here's the part where you take the negative 6, you divide it by 2. We're taking the coefficient, we're dividing it by 2. We have to do a little bit of extra fraction algebra. Gives us this. Then what do I do with the b over 2a? I square it. So when I square this, don't I get plus b squared over 4a squared? Yes? Okay, so now let's take a bite out of that. Digest it. Ask me questions. Those of you that weren't here, this isn't going to be as fresh for you, but this was the math that we did on Friday. This is now a super algebra problem involving it. Yes? Because in order for me to factor out an a, to make this a 1x squared definitely, I have to take this one and divide by the GCF. You know what I mean? Like, if this was a 10 and I took a 2 out, I would have to do 10 divided by 2 and make this a 5. So this is the symbolic form of all that. Okay? We're going to go somewhere with this. And it's not going to be too wacky. You'll never have to recreate this process again. But sometimes just this upper algebra understanding does help you down the road with more complex algebra. Now, if you remember, we talked about the fact that in our little seesaw example, okay, I really didn't add b squared over 4a squared. Didn't I really add to this side positive b b squared over 4a. When I multiply a times this is what I really made the net change on the right as. Yes? So how do I balance adding this? I subtract that. B squared over 4a. You know, I know there's somebody sitting there saying, well, wait a second, you wrote 4a squared. Why do you only have a 4a on the outside? Anybody explain why I just have a 4a on the outside, not 4a squared, to balance it? Everybody's okay with that? We're all good. All right, where'd I lose you?
The last part.
Okay. So on Friday, we talked about completing the square to change the form of a quadratic. Okay? So since I interjected the orange here, okay, when you look at it, in a pure sense, it looks like I'm adding just b squared over 4ac. But if I redistribute this a, my real change to the right side of my equation, so we talked about like a seesaw, meaning like an equal sign, what I really did to the right, I balance that by taking a times this, which is why the a's canceled to reduce here, and I use a subtraction sign. Now I have a balanced equation, because now I did negative b squared over 4a at the end. Yes? Yeah.
Is there anything
Because I took a times b squared over 4a squared, which gave me that.
Is it minus because that one's positive?
Yep, right. So I want my net change on the right of my equation to be 0. So if I'm interjecting, adding, subtracting, multiplying, dividing, if I'm doing that and it wasn't there to begin with, I have to balance it, or I have to add the same thing to the other side, which when I bring it back over results in opposites. So it's the same idea. Yes?
after you write the new term, do you keep the a in the front?
Yep, we're going to keep the A in the front. So here's what I'm going to do. Does anyone need the orange yet? Does that make sense where I got this orange term from? That was my explanation for that. So if I get rid of this here, and I rewrite this, and I'm going to try to use some colors here. Here's your A, right? In the middle, in here, I'm going to get plus b over 2a squared plus, and then down here, this is like a combined. You're going to say, oh my gosh, that looks really, really weird. However, if you understood what we did with graphing and parabolas, wouldn't my vertex be at negative b over 2a? My vertex would be at negative b over 2a. Yes, the opposite of whatever this is. Does that make sense? That's where we need to be with today. The fact that we can transform in an abstract form to here, which this is a formula. If you want to ever find in any given general form, you want to find the x of the vertex, you can use negative b over 2a every single time. Never changes. Yes?
I get that, like, in the parentheses has, sorry.
This parenthesis or black?
Yeah, that one.
Mm-hmm.
So I understand that, like, if you square it, like, it's the same, like, x squared and then b squared over 4a squared, but, like, what happened to b over a?
What would be over a?
Like, see how it's b over ax? Like, in the first one, where did that go?
Here?
Yeah, well, like,
Well, because when I complete the square, whatever I get when I take this and divide it by 2, take your b term, divide it by 2, that's what always goes in here for the, like, to create the perfect square.
okay, so you're kind of, like, ignoring it? Like,
I'm not ignoring it. I'm saying this. Like, what we did is we would do things like x squared minus 6x, and then over here we would have, like, a plus 10. Okay, so my original problem was x squared minus 6x plus 10, and I'm asking you to complete the square. So I would separate the first two terms, and then we worked on completing the square here. We calculated up here that this was a plus 9. To balance the plus 9, we would do a minus 9 at the end. This is all in the notes from lesson 1. So then you would turn this into x minus 3 squared. If I FOIL this out, I get this. I'm changing the form of what's in the box into perfect square. And then down here, this gives me a new +1. So my vertex would be at 3, 1. Where my A value is 1. I didn't have to factor anything out.
So if you factor that, you will have the B over AX, right? Like that, the problem to your left. Like if you were to factor that.
If I put it back in, multiply it back, you'd have to FOIL this first. Then you would have to multiply.
And then get the same thing up top.
You would get what you get here, which then you could go backwards and get here. Okay? But the idea, what I'm trying to show you, is that given any quadratic in general form, ax squared plus bx plus c, we can find the vertex, the x of the vertex, by using the formula negative b over 2a. And I understand in the past, you probably came into class and that's exactly what your teacher would say to you. That would be the very first slide. Here's an equation. If you want to find the x, all you have to do is this. Fantastic. But there's a reason why it works, and being able to do some of this higher level algebra is going to be essential to those of you that want to go to calculus, those of you that want to be engineering majors where you're going to have 4 and 5 variables to deal with. So you have to start, being able to work with things and understand and apply processes to things that are not just pure numbers. So we're just exposing you to that. But the big idea is, and I repeat for the 3rd time now, given general form, you can find the x of the vertex by using the formula negative b over 2a. Got it? So right there, in your notes, it says, we know the one coordinate of the max or the min, depending if the vertex opens up or down, the parabola. X will always be found by using negative b divided by 2a, the x of the vertex.
So, which one would?
Okay, so time out. Here is general form. Okay, general form. The first skill we worked on Friday was taking general form and going to what's known as standard or vertex form. So we know the vertex here, by changing this form, is 3, 1, correct? That makes sense. Okay. What I'm saying is, right from here, I could have said, hey, what's the x of the vertex? You could have taken this and said negative b over 2a, and you would have still gotten 3. Formula.
So, which one would be your final answer? Like the one with the
This
text one?
this black line here
Yeah.
is the vertex form formula for any general equation. Okay? But we're not trying to get that. All I wanted to get to was this proof that the x of the vertex, which comes from this part of that form, of this new form, is right here. Like, that's where it comes from. So the big idea, right at this point, we can go from here now to here. Memorize that. That's where we need to be. You're never going to have to prove this again. You're never going to have to do it on your own. None of that. Okay, this is just an exposure to that higher level algebra. Okay. Those of you that are panicking, don't. It's going to be okay. Let me show you what I mean. If we move forward, it says here to find the max. Okay, so I'm going to erase all of this and all of this here. Okay. Find the max or minimum algebraically. Right? So anytime we see that, yes, you could complete the square, but you're going to probably be given problems that aren't very nice to complete the square with. So we can go right to our formula, which is this. Right? So, do I have general form? Yes. What are my key values? Well, A is 1, B is negative 2, C is negative 8. So A, B, C. The max or the min is another name for the vertex. In number 1, do I have a max or a min based on the general equation? You should be able to tell me that by looking at it. Minimum, because A is 1, which means it's a standard parabola that opens up, 1x squared. Okay, we know that because A is 1. That also means that when we plot the vertex, over 1, up 1, left 1, up 1, we learned that in the last unit. So now I can use my formula, negative b over 2a. So negative b over 2a is going to translate to negative 2 over 2 times 1. Watch your signs when you do this. That's going to give you 2 over 2 or 1. So the vertex, you told me minimum, is going to be located at 1 comma something. Did I lose you or are you okay? That part makes sense now, right? It's easy. It'll be a little harder with decimals, so just watch your signs and all that. Now that all this other stuff's gone?
Yeah.
Okay. Plug and chuck. All right, now, if I tell you the x is 1, how can I figure out the y based on my equation? Just plug it back in. Exactly right. So to figure out y, I'm going to get 1 times 1 squared minus 2 times 1 minus 8. What does that give me? 1 minus 2 minus 8. Negative 9? Negative 9. So my minimum would be located there. Okay, now, let's take a look at what we've really done here. We found the vertex without completing the square. We know it opens 1. We could graph it from here, right? You know your base equation is y equals 1x squared, so you're good to go. Right? Number 2. Number 2 is an awesome problem not to have to complete the square on. It really is, right? Because if not, I got to factor a 4 out front, then I got to complete the square, and then I got to balance with that teeter-totter thing. It's just, it's so much work. Can't I just use the formula? Absolutely you can, unless it says solve by completing the square. So in this case, this is my A, this is my B, this is my C. Why don't you do this one? Figure out the vertex. Tell me if it's a min or max. Follow just like you did on the last one. When you're done, please do not turn the page. Hi. Oh yeah, thanks. Where'd you find it? Do you know where it was?
No.
Somebody just
Oh,
turned
Mr.
it in?
Bomber.
All right.
Just have to count on his fingers too.
Negative 41?
I got negative. Oh. I'm not even gonna answer.
Yeah, it's 4. 16 minus 32 minus 9.
Considering.
Negative 25? Is that better? Negative 25? Yes? Okay. So, the 2 examples we just did, the first one we could have done by completing the square pretty quickly. The second one would have been a little extra step with factoring out the 4 and then balancing the equation. The reason why we teach you this method is the following. Why do we have to take recalc? Because we're going to start to model real-world examples, like legit, honest-to-God real world. And when you do that, this is the kind of equations you're going to get. So notice, if you were going to complete the square, you would have to factor out a 0.0032 from your first two terms, which is just ridiculous. Nobody can do that. Yes.
Yeah.
Okay, so if you take a look, this is an example. We know it's a parabola because it's x squared, right? Pretty obvious, but it's not going to be maybe as nice as something we've seen before. You may or may not have a graphing calculator to do this problem. Hint, you will not have a graphing calculator, so you can't graph the path of it or do anything else. So in order to answer a question like this, you're going to need to use the formula, right? What I'd like you to do, please, is turn the page, read the word problem. You may work by yourself or with a partner. There are prompts that will help you as you go through. And I want you to go all the way down steps 1 through 7. All right, one of the things that I'm going to ask you to start doing for your word problems in this unit and every unit moving forward is you need to start thinking globally, not locally. So what that means is when you read through, you really need to characterize what the story is about, who the players are, and the relationship that they're trying to explain. This problem does a really good job of kind of expounding on that and telling you exactly what each variable means. So when you read the problems and you do that, it's a good idea to do a sketch of your axes to label them. Also, you've got the units question. Are we talking about distance in inches? Are we talking about feet? Are we talking about miles? All of that will come into play when we get into the trig. So here's our example of that. This is going to be a parabola. Okay, if you open it, notice that if all of x is 0, my y-intercept is going to be 3. We knew that from what we did on Friday. Okay? So what was being measured along x? What was the x-axis? What does x represent? The distance from, that the ball is from home plate, correct? The distance in feet? Yes? The distance in feet? So technically what we are looking at is what's called a cross section. So it doesn't matter if the person is hitting the ball and it's going out to left field or to right field. We're trying to get that snapshot from the side of the exact path of the ball. Y is going to be the height, correct? The height of the ball. And that also is in feet as well. Okay, so that's kind of nice that our units are the same, not any different. So you'll see, why do you think that they started at 3 feet? Right. So if we were golfing, it would start at maybe 2 inches, right? If you take a look at this, those are the kind of pieces that when you read the problem, you just want to make sure that it makes sense to you, that, applying exactly what's going on in the story to what we're seeing in the graph. So what does the x-axis represent? What does the y-axis represent? Makes sense that we have a parabola, correct? I mean, that's interesting. We talked about the fact that we can find the vertex point by using our formula. We find the x using negative b over 2a. We then take that x value and plug it in. Now be careful. Oftentimes in word problems like this, they're going to ask you, well, what's the maximum height that the ball reaches? That's going to be a 2-step problem because obviously you have to use the formula to figure out the distance, then plug it back in order to get the height. So don't be confused that you just go negative b over 2a, that's what we're doing, that's the answer. That's not going to answer the question that they were necessarily asking. So work-wise, let me give you your answers. If you plug into your x, you should have gotten 156.25. To figure out y, we take the 156.25, we plug it back in and get 81.25. So this is our x value, this is our y value, so that is the height of the ball. Yes?
For x, I just left it 1 over 0.0064. Can I do that, or do I have to?
Yeah, you should get the same thing when you do to get to here. Just be careful because if I were asking you what is the distance,
Okay.
that wouldn't really be a user-friendly answer that we could talk about. Okay, now, this is another part that is going, those of you that are going to calculus, you're going to see this all of the time. They're going to ask you questions about How far does the ball travel until it reaches the ground? Okay? That purple dot is a very special point because it means that the ball reaches a height of 0. We're also making some assumptions in this word problem. That when the ball hits the ground, that it doesn't roll, right? It just deadens and stops, which doesn't really happen normally when you hit the ball. So there are some, things that we're taking for granted here. At that point, what do we know about a ball that's laying on the ground? It has 0 what? Height, correct? It has 0 height. So because of that, we know automatically that the height, which is the y value, is going to be 0. We want to figure out what the x value is. So that relationship is one that you're going to have to study if you don't see it right away. Anytime I ask you to find a point that is on the x-axis, that's y equals 0. If you had a graphing calculator, you put it in for y2. If we're doing it by hand, the answer you should get is 315.47. Well, how the heck did you get that? If I replace f of x, which is my variable that represents y, because I'm dealing with function notation, and I go to solve this, again, this is a, 1 is b, c is 3, and we're going to go to the quadratic formula. You would need a calculator to do that. When you do that, you're going to get a value negative b plus or minus b squared minus 4ac, all of which is over 2a. Remember, you're going to get the plus the square root, which is the right side, and then you're going to get a minus the square root, which is going to be the left side. We want the right side in this case. The other thing to be careful of is in this example, okay, when I get 315.47, what did I get for my x value of the vertex? 1 what? 150.25. Notice I can't just double that, and the reason I can't double it is because this didn't start at 0, 0. If it started at 0, 0 and came up and down, then I would have that mirror image that to the middle would be halfway, and then to the end you could just add to itself. But I don't have that here. And that comes from the fact that this started at 3 feet, and actually my other intercept is to the left of the origin. Yes?